Okay, so we should be live. Yay. Hello, world. We're going to write some code. We're going to talk about some code and probably do a little bit of writing. So chapter 7, sharing role behavior with modules. The last chapter was about, sharing behavior with inheritance. And now we're going to talk about sharing, code with modules, sharing behavior with modules. So, So I'll read the introduction paragraph here. So the previous chapter ended on a high note with code that looked so promising. You may be wondering where it's been all your life. However, before you decide to use classical inheritance to solve every imaginable design problem, consider this. What will happen when fast feed develops a need for recumbent mountain bikes? Blah, blah. So like with any design technique, there's always trade-offs. So you just got, it talks about, again, there's always trade-offs. Creating the most cost-effective application requires making informed trade-offs between the relative costs and likely benefits of alternatives. So this chapter explores an alternative that uses the techniques of inheritance to share a role. It begins with an example that uses a Ruby module to define a common role and then proceeds to give practical advice about how to write all inheritable code. So yeah, I mean, we could solve this problem with using the same thing we did in chapter 6, right? Classical inheritance. But, it says use of classical inheritance is always optional. Every problem that it solves can be solved another way. So just got to think about, if I do it this way, what are the benefits? What trade-offs am I making? Alternatives? Are there any alternatives? Right. So you can probably spend more time thinking about that, how to implement code, than the actual implementation. So understanding roles. So some problems require sharing behavior among otherwise unrelated objects. So last chapter with the inheritance, we had related, was it last chapter? Yeah, acquiring behavior through inheritance. So I forgot what, it's been 2 weeks. I forget everything after a week, and it's been 2 weeks. So, so we had a bicycle class, and did we do? Oh yeah, and then we had a mountain bike. We had a road bike. So we solved this problem. So we had bicycle, and we had different types of bicycles. So we used inheritance to solve that problem. Now, mountain bike and road bike, they're related classes, right? They're obviously a subtype of bicycle. And so we could share code. We can acquire code through inheritance that way. Share code to the subtypes through inheritance. But what if we have objects that are not related? What if we have a mountain bike and we have a car? A car is not a bicycle. It can't inherit from bicycle. But let's say they have code in common that could be shared, like we want to dry up our application. So this is what this chapter is about, sharing common code between classes that are not related. So when formally unrelated objects begin to play a common role, they enter into a relationship with the objects for whom they play the role. So we're gonna, find a role that exists between unrelated objects, and we're gonna implement that role. So using this role, creates dependencies among the objects involved, and these dependencies introduce risks that you must take into account when deciding among design options. So this section unearths a hidden role that creates code to share its behavior, while at the same time minimizing the dependencies. Okay, so finding roles. So if you think back to chapter 5, we reducing costs with duck typing. We had we created a duck type, and it was a preparer. The preparer was a mechanic. Let's see. Yeah, so the preparer duck type is a role. Objects that implement preparer's interface play this role. And the objects were mechanic, trip coordinator, and driver. They all implemented the prepare trip. So each one of those preparers could prepare the trip. Therefore, the objects can interact with them. Other objects can interact with the preparer without concern of the underlying class. So, and the existence of a preparer role suggests that there's also a parallel preparable role. And the preparable role is played by the trip class. The trip is preparable. So the trip class acts as a preparable in chapter 5 example, and it implements a preparable interface. This interface includes all of the messages that any preparer might expect to send. If you remember, the preparers in these 3 classes, mechanic, trip coordinator, and driver, they would send messages, bicycles, customers, and vehicle. And so they sent that to a preparable class. So we only had one preparable class in chapter 5, but it's, we could actually have more preparable classes. So there's a role there. Preparable role is not terribly obvious because trip is its only player, but it's important to recognize that it exists. Then chapter 9 suggests techniques for testing and documenting the preparable role so as to distinguish it from the trip class. So although the prepare role has multiple players, it is so simple that it is entirely defined by its interface. To play this role, you only need to implement prepare trip. Objects that act as preparers have only this interface in common. They share the method signature, but no other code. So preparer and preparable, they're perfectly legitimate duck types. It's far more common, however, to discover more sophisticated roles, ones where the role requires not only specific message signatures, but also specific behavior. So these roles, that it's talking about this because these roles, prepare and preparable, they had common method signatures, but did not have common behavior. Their behavior was different, but they had common method signatures. Next, we're going to talk about when roles need to share common behavior. So when roles need shared behavior, you're faced with the problem of organizing the shared code. And that's where modules come in. So ideally, this code would be defined in a single place, but be usable by any object that wished to act as a duck type and play the role. So many OO languages, provide a way to define a named group of methods that are independent of class and can be mixed into any object. And in Ruby, you might hear them be called mixins, and they're called modules. So methods can be defined in a module, and then the module can be added to any object. So this is how we can share behavior between classes that are completely unrelated. So once you start putting code into modules and adding modules to objects, you expand the set of messages to which an object can respond, and we enter a new realm of design complexity. So an object that directly implements a few methods, or in Rails, if you've ever seen a Rails object inherits code, you can see no methods that it inherits, like from active record. If it's a subclass of active record, you don't have to implement any methods, yet you get a lot of methods for free. Right? So an object that directly implements few methods might still have a very large response set, such as an object that inherits from active record. So the total set of message to which an object can respond includes those it implements directly, those implemented in all objects above it in the hierarchy, such as its superclasses, those implemented in any module that has been added to it, and those implemented in all modules added to any object above it in the hierarchy. So at the end of the chapter, we talk a little bit more about this, how, Sandy talks a little bit more about how a method is resolved. So if you're not, so far we know that when a method gets called, it checks its class. If the method's not in the class, and it checks its superclass all the way up until object, right? That's the simplest explanation. That's how all OO languages work. But in Ruby, it's not that straightforward. It's not that simple, and we'll talk more about that at the end of the chapter. So organizing responsibilities. So here we go. So we're going to get into an example here and start writing some code. So consider the problem of scheduling a trip. So the company Fast Feet, they want to be able to schedule a trip. They want to, if they have a trip that's coming up, they need bicycles, they need mechanics, and they need a vehicle, right? So they need to make sure they're all available for that trip. So Fast Feet needs a way to arrange all of these objects on a schedule so that it can determine for any point in time which objects are available and which are already committed. So obviously bikes, mechanics, and vehicles, they're real world things in the physical world, and they cannot be in two places at once. And furthermore, they need some downtime, right? Bicycles, so the requirements are that bicycles have a minimum of 1 day between trips. Vehicles, a minimum of 3 days, and mechanics, 4 days. So the code to schedule these objects can be written in many ways. And as has been true throughout the book, this example will evolve. It begins with some rather alarming code and works its way to a satisfactory solution, all in the interest of exposing likely anti-patterns. So assume that a schedule class exists. This interface already includes these three methods. All right, so we got a scheduled method. So we got a class, the schedule class. It's got a scheduled method. It takes in, there's some loud noise. I'm not sure who it's coming from. So I'm gonna mute you guys. All right, so there's a schedule class. It's got a scheduled method. It takes in a target, starting and ending time. And then we can add to it. It takes in a target, starting and ending time, and we can remove from the schedule. It takes a target, starting and ending time. So each of the above methods takes 3 arguments. So the schedule is responsible for knowing if its incoming target argument is already scheduled and for adding and removing targets from the schedule. These responsibilities rightly belong here in the schedule itself. These methods are fine, but unfortunately there's a gap in the code. So if we were to write a sequence diagram for this, it would look like this. We've got an instigating object. So that object's going to say, hey, you know, is the bicycle free for this start and end time? So it's going to send the message, is the bicycle schedulable to the schedule class. The schedule class knows that a bicycle has needs a downtime of 1 day, so it takes that into account and returns a response. Likewise, you know, if it gets a mechanic class, it knows that if the mechanic needs a downtime of 4 days, figures that out, responds. So you can see here that in the schedule class, it's doing a type checking, right? It gets a target, it checks the target's class. If it's equal to bicycle, it knows that it needs 1 day. If it's equal to mechanic, then it knows it needs 4 days downtime. Vehicle, 3 days downtime. So I just muted you. So I'm going to ask you a question now. So if you want to answer, unmute yourself and let me know. So is there anything here that you see is could be improved? Or do you see an anti-pattern here?
You're not sharing your screen?
Oh, okay.
Yeah. I think
I can say the checking of the class.
Yes. Yeah.
I think that for now.
Yeah, whenever you're checking a class, whenever you're doing this type of type checking, it should be an alarm bell going off in your head, right?
Mm-hmm.
So what can we do? So, I mean, the easiest thing is that we should just be able to ask bicycle, right? Hey, hey, bicycle, are you scheduled for this day, right? Instead of having, you know, we should just be able to send a message, right? You should be able to think, hey, I should just be able to send a message to bicycle instead of having to check that, hey, what class is this? And then I have the algorithm. I should just let bicycle handle that, right? I should just be able to ask bicycle, hey, so bicycle, you know, are you doing anything Friday? Right? So yeah, try to think in terms of sending messages. So yeah, anytime you see a type check, it should be an alarm bell going off. So yeah, so the schedule class is checking what class the target is, and then based on that, you know, it knows how many lead days to apply, and then it checks. Okay, so I got this target. I've got the starting date minus the lead days, you know, and the ending date, and that will tell me if it's scheduled or not. So the schedule in figure 7.1, the schedule knows the lead time for other objects. So we've seen this pattern of checking class to know what message to send. Here, the schedule checks class to know what value to use. All right. So it's checking the class to know what behavior to apply. So in both cases, schedule knows too much. This knowledge doesn't belong in schedule. It belongs in the classes whose names schedule is checking. So this implementation cries out for a simple and obvious improvement when suggested by the pattern of the code. So instead of knowing details about other classes, the schedule should send them messages. We're removing unnecessary dependencies. The fact that schedule checks many class names to determine what value to place in one variable suggests that the variable name should be turned into a message, which in turn should be sent to each incoming object. So let's do that. Let's write up this code, and then I think it's got to, I think there's code in here somewhere. I didn't pass it. Yeah, no. Okay, we're getting to it. So discovering a schedulable duck type. So figure 7.2, which is this figure right here, shows a sequence diagram for new code that removes the check on class from schedulable, from the schedulable method, and alters the method to instead send the lead days message to its incoming target argument. So this change replaces an if statement that checks the class of an object with a message sent to that same object. So let's see what it does. So here we got the instigating object. Instigating object still sends the same message. Hey, is this target schedulable for the starting and ending time? And now the schedule class, instead of knowing the lead days for the target, is going to ask the target, it's going to just send, it's going to take that target, it's going to send the message lead days, it's going to ask the target for the lead days. So it no longer needs to check the class of the target, it doesn't care. And then it can just send the message, okay, here's the target, it can do its calculation, starting minus lead days, ending, and is it scheduled or not? So with this simple moving of the method lead days to the target class, we got rid of all that type checking. And we've done that in the past, in the previous chapters in the book. We've done something similar, right? So are we done? Can this be improved more? What do you think? We're obviously not done, but do you see anything that there's still something hiding here? There's still some more improvement that can be done. Well, let's continue. Give you a hint. It has to do with this method here. But let's continue. So the schedule expects its target to behave like something. So yeah, so here it's talking about the lead days. The schedule expects its target to behave like something that understands lead days, right? So that is like something that is schedulable. So we have discovered a duck type, right? So here, this is a duck type, right? This is schedulable. These targets are schedulable, and they should have the lead days method implemented on them. So right now, this new duck type is shaped much like the preparer duck type from chapter 5. It consists only of this interface schedulable, which must implement lead days. We currently have no other code in common. But since this chapter is about modules, it's soon going to have behavior that's in common. So discovering and using this duck type improves the code by removing the schedule's dependency on the specific class names, which makes the application more flexible and easier to maintain. However, figure 7.2 still contains unnecessary dependencies that should be removed. Again, this is figure 7.2, and this still has dependencies that should be removed. So let's get into that. So it's easiest to illustrate these dependencies with an extreme example. And I really like this example. So we all work with strings in object, like in Ruby, right? Specifically in Ruby, not Python, but in Ruby. If you want to know the length of a string, you just send it a message. In Python, you actually pass it into a function. But in Ruby, you just send it a message. And if you want to know if the string is empty, you can just send it the empty message, right? But let's imagine that we have a string utility class that implements utility methods for managing strings. So you can ask the string utility class if a string is empty by sending string-utils.empty, and then you pass in some string. So if you have written OO code, you will find this a bit ridiculous, right? Using a separate class to manage strings is patently redundant. Strings are objects. They have their own behavior. They manage themselves. Requiring that other objects know about a third-party string utilities to get behavior from a string complicates the code by adding an unnecessary dependency, right? String utilities is an unnecessary dependency. We've created a third-party class to add behavior to the class that we need the behavior in, right? So this specific example illustrates the general idea that objects should manage themselves. They should contain their own behavior. So again, if your interest is in object B, you should not be forced to know about object A if your only use of it is to find things out about B. So let's go back to the sequence diagram. Our interest is in the target here. Like in, what is this? We got so our targets, just to put this into visualization, our targets are like a bicycle class, a vehicle class, a mechanic class. So if we have a vehicle class, we want to know if it's schedulable. Why? So here we're depending on a third-party schedule class to determine if our vehicle is schedulable. Wouldn't it be easier just to ask vehicle if it's schedulable? The instigating object could say, hey, vehicle, are you doing anything Friday night? You want to go out? So that's the next improvement that we can make. Instead of depending on this third-party class here to determine if, that's kind of like asking, vehicle's parent if vehicle can go out Friday night. But anyway. In some cultures, maybe this might be the right way to do things, but we're programmers. We just want to get the job done.
Yeah.
So the sequence diagram in figure 7.2 violates this rule. The instigator is trying to ascertain if the target object is schedulable. Unfortunately, it doesn't ask this question of target itself. It instead asks a third-party schedule. So asking schedule if a target is schedulable is like asking string utils if the string is empty. So it forces the instigator to know about and thus depend on the schedule, even though its only real interest is in the target. So writing the concrete code. So here, so as it currently stands, the schedulable role contains only an interface. Yeah, so the schedulable role. So remember, if anything, so vehicle, bicycle, and a mechanic, they're all schedulable. They all have this schedulable role. So as it currently stands, they only have an interface, which is, to find their lead days, their downtime. So adding the schedulable method to this role requires some code, and it's not immediately obvious where this code should reside. So yeah, so we need to write some code, right? So what we want to do is create something like this sequence diagram. So we got an instigating object, and we're just going to say, hey, are you schedulable during these days? And the bicycle is going to receive that message and say, okay, well, I know my downtime. Well, let me check the schedule. Let me check my trip planner. Let me check my schedule. See if I'm free Friday night. So it's going to check its schedule, and bicycle, is going to say, hey, schedule, I need this many downtime, and here's the start time and end time. Am I available? It's going to, say, pass in itself, since it wants to know about itself, and schedule is going to return whether or not, it's doing anything Friday. So instigating object just asks bicycle, are you free? Bicycle's going to, check its schedule and determine all that stuff by itself, and then return the answer to the instigating object. So so now you can see schedule is pretty much only doing one thing now, right? So first we had a schedule class that's doing a lot of different things, and now it's doing one thing. And we've moved all the behavior into bicycle, where it should be. So the thing here is that not only bicycle needs to implement this behavior, but any object that is schedulable needs to implement this behavior. So again, mechanic and vehicle also needs to implement this behavior. So we need to decide what the code should do and where the code should live. So the simplest way to get started is to separate the two decisions. Pick an arbitrary concrete class, for example, bicycle, and implement the schedulable. And that's what we did here. And then once we've done that, then we can refactor. And so before this change, every instigating object had to know about and thus had a dependency on the schedule. Now this change allows bicycles to speak for themselves. Bicycles no longer have to ask their parents. They can speak for themselves. And then freeing instigating objects to interact with them without the aid of a third party. So, all right, so here's some code. So the code to implement this sequence diagram is straightforward. Here's a very simple schedule. Obviously, this is not production ready because it always returns false, but this is an example. But so we're here so let's get writing some code. So after we spin up this code, after we write it, we're going to do some refactoring, and that's where the modules will come in. So, all right. I need to start collaboration session. I don't know why I have to do this over and over again.
Yeah, that's the problem with this code. You have to log in.
Allow an extension. I already opened. Didn't I?
I think it happens when you shut down. When you don't, it doesn't. I don't know.
Oh, okay. Okay.
Yeah, it's
Wow.
encouraging us not to shut down our computers.
Yeah. Yeah, that's not going to happen.
Yeah.
All right. There's the link. So yes, this is good. This is right where I wanted to get to today. It's perfect. So let's see, I got the bicycle class up. Let's see. Well, what do we need? We need to create a new class, schedule. So I'll go ahead and see, what am I doing here? That's fine. So let's do OS. Okay, so touch chapter 6, and we'll put in schedule.rb there. And then there we go. We got our schedule class. So how do I see who's logged in? I guess nobody's logged in yet. All right. Hey, Gideon. Yeah, so if you want to start typing up the schedule class.
Yes. Can you leave the book open?
Yeah, I'm trying to get it on the same screen here. Can you see it?
Yeah, I can see that.
All right.
And I'm not able to join you.
Okay.
Yeah, I'll restart my VS Code.
Yeah. All right.
Microsoft.
Let me see. I'm gonna get more real estate here. All right. Looks good. Do you want to do the code in Bicycle too? We'll need to add. So yeah, so the bicycle class here. Oh, hey, Mike. Maybe Mike wants to do it, or whoever. There's two methods, and we need to update the attribute reader. So perhaps Mike can do the initialize method, and Gideon, you could do the schedulable method.
Okay.
And I can do the easy one. I can update the attribute reader. All right, I'm done.
No, you cheated.
Hurry up, you guys.
Okay.
I'm waiting.
Cheated.
Hey, hello.
Hello?
Yeah.
You got kicked
So
out again, or?
Yeah, nope.
Oh, okay.
I just did get a good introduction. So I should do the initialize.
Oh, yeah, we just actually, looking at it, we just need to add line 6.
Okay.
We need to add line 6 to the initialize method.
So we have bicycle, then we need to add line 6. Schedule equals add schedule.
That's all right. These are all indented wrong. We can go like that, actually. A lot of this is indented wrong. Oh, well.
Yeah, it's using 4 spaces.
Yeah. I blame Mike. Mike must have written this code.
Yeah, with Python in mind.
Yeah. Yeah.
Yeah. This scheduled it new?
Yeah, schedule.new. Perfect. All right, so we got our code written. Everything should work. Let's go back to the book here for a second. So yeah, so the code to implement the sequence diagram is straightforward. Here's a very simple schedule. So we did that. So anything we pass a schedule is going to be it's just automatically going to say it's not scheduled, so it's available. And then this next example shows bicycle's implementation of schedulable. Right, so we need to, so we go back to the sequence diagram. So bicycle needs to implement the schedulable method, which takes a starting and ending string. And it also needs to know, bicycle also needs to have lead days implemented, right? So let's do that. And then it also needs to talk to schedule. So that's where the initializer comes in, right? So we initialize the schedule. So bicycle, as it is now, bicycle depends on schedule. That's a dependency, right? Because we initialize the schedule class. We initialize the schedule object inside bicycle. So this is a dependency. Wherever bicycle goes, schedule needs to come along. So let me expand this. So yeah, so we got the initialize, we got the schedulable, and now we need, so schedulable basically, delegates, it takes in, start date and end date, and it adjusts the start date to include the downtime. It requires some downtime. So, and then it just passes that to the scheduled method. And if it's scheduled, if it returns true, then it inverts that and says, sorry. It returns false and says, sorry, we're not scheduled. If it returns false, and it returns the schedulable returns true, right? So that's what we got going on. So we still need to implement the scheduled method, and we need to implement the lead days method. So I don't know. Let's get that done. Whoever's
I'll go for lazy.
all right. So Mike, can you do the scheduled class? Thanks. Woohoo.
Is it not just a method?
So yeah, so line 17, then line 19.
Okay. Yeah. My instincts are going for the semicolon.
So yeah, so this method is gonna delegate. It's gonna check its schedule. You don't need the @ symbol because we got it as an attribute reader. And then schedule has the method scheduled. Man, they sure spell schedule weird. Is that the right way to spell schedule?
So it's
Yeah, I think so.
so
That looks weird to me. It's one of those things.
So you ask it looks weird.
schedule, but schedule.
Schedule. I think we should just spell it with a K. SK.
Yeah, you American corrupted English.
If I start
So
doing
that's all we
it,
need to do.
everybody will start doing it. Yeah. And then we can test this by writing this code here, lines 30 to 35. Let's do that. I'm going to do that right here. Wait. What's that? Oh, yeah. So let's do that. I'm going to do it right here. Well, no, let's just put it at the bottom. I think that's where all our code is anyway, so.
Yeah, the file is sort of going big.
So here, if we require date, and then we give it a starting date, which is equal to date.parse, and say 2015-904, and then give it an ending date, date.parse, and say it's going to be 2015-09-10, and then we instantiate bicycle, and then we're going to check, okay, so is this bicycle schedulable? We pass in starting and ending. Then if we run this code, I should puts, right? Maybe let's puts this out. And yeah. Actually, no, we don't need to puts anything out.
Yeah. Because you have puts in schedule.
I'm running the wrong one, huh? Okay. I need to be running the bicycle class.
Yeah.
Bicycle.rb. There we go. Okay, getting something. Uninitialized constant bicycle, schedule, name error. So from line 110, e equals bicycle dot. Oh, I need to pass in So remember, so we need to create a schedule class too, right? So what was it? Args schedule. I'll just pass in schedule.new. I gotta pass in my schedule because only Bicycle has. I don't know. Anyway, it's gotta pass in the schedule.
Oh, do we need to require that schedule in this file?
I think something like that, right? Doing something wrong.
The schedule is in another file. Probably it's not within the scope, yeah.
Right. So let's
Or we can just copy that schedule that class to this file.
yeah, need to require yeah, let's just do that. Copy this, we'll put it right here. All right. So now when we run it, this bicycle cannot respond to default tire size dot implemented error. Oh, right. Because yeah, you're doing bicycle. Let's do road bike.
Yeah.
Still a bicycle. Here we go. This road bike is not scheduled between. You see that?
Yeah.
So, all right, it's working. So, because yeah, bicycle is not meant to be instantiated because we made it an abstract class. So perfect. So yeah, so this bicycle is not scheduled between such and such dates. And you get back true. So running the code confirms that bicycle has correctly adjusted the starting date to include the bicycle specific lead days. So yeah, we can see that it did include the lead days, right? September 3rd and September 10th through September 10th. Because the bicycle has 1 day lead day, so cool. So now that we've put this code into bicycle, so if we take a look at this, we've got the scheduled method. We've got some behavior here, right? Not just methods. We've got behavior that's going to be common to any class that needs to be scheduled. Right. So the vehicle and the mechanic, they both need the same behavior. They're going to use not just the method name. They don't just need to implement this method, but they need to implement the same behavior. Right. They're both going to check their schedule, take lead days into account, pass in an end date. And they're both going to send that method to scheduled. And they're both going to have slightly different lead days, but again, they've got behavior that's common to all three. So the next part of this book is to extract this, extracting the abstraction. So the code above solves the first part of current problem in that it decides what the schedulable method should do. The bicycle is not the only kind of thing that is schedulable. Mechanic and vehicle also play this role and therefore need this behavior. So it's time to rearrange the code so that it can be shared among objects of different classes. So the following example shows a new schedulable module, which contains an abstraction extracted from the bicycle class above. The schedulable, so the schedulable method on line 8 and the scheduled method on line 12, they are exact copies of the ones that are implemented in bicycle right now. The only two things have changed from the code as it previously existed. The first is line 4, scheduled method. Line 4 has been added. This method returns an instance of the overall schedule. Before we were doing this in the initialize method. But modules are not meant to be initialized. So we can just put it into a method here, to a method call. And then we can, and then back in figure 7.2, the instigating object depended on the schedule, which meant there might be many places in the application that needed the knowledge of schedule. In the next iteration, figure 7.3, this dependency was transferred to us. So I don't know if you want to take a look at those figures. So figure 7.2 looked like this, where the instigating object, depended on schedulable and passed in target. So the instigating object depended on the schedule, but now it's been moved to the target class depends on schedule. So it's improved. Second change is to the lead day method. The lead days, as you can see in the module, just returns 0. In the module, even though we expect, people who include this module, schedulable, to override lead days, it still needs to implement it because, let's see, Sandy says it much more sufficiently than I do, but because, it has this method, because it has this method, within its methods, it needs to implement it. Even if it just says, even if you just raise a not implemented error, you need to implement this method. The same reason why we implement the local spares method in bicycle. All it does is raise a not implement error, but we need to implement it because it's part of its public interface. So yeah, even if there were no reasonable application default for lead days, the schedulable module must still implement the lead days method. The rule for modules are the same as for classical inheritance. If a module sends a message, it must provide an implementation, even if that implementation merely raises an error indicating that users of the module must implement the method. So now that we've extracted that behavior, all we need to do for bicycle to have that behavior is include schedulable, and we can override the lead days method. And that's it. The lead days method is a hook that follows the template method pattern. And bicycle overrides this hook on line 4 to provide a specialization. So I kind of want to stop here, and we'll continue next week. Doing the extraction of this code and creating our module and including that module in the schedulable classes. Mm,
Yep.
yeah.
Okay.
And then we'll wrap up chapter 7. And we'll talk more about how we can even investigate it if we want to see how methods and modules, like when do they get called, right? We know when a method is implemented in a class, that will get called first before a method in the superclass. If the same method is implemented in a superclass, the method in the class gets called first, and the subclass gets called first. And if you've got the same method in a module, or if you've got even same methods and modules that are part of the superclass, when do they all get called? How are they a part of the hierarchy? So we'll get into that in more detail too next week.
Yeah, that sounds interesting.
Yeah. Nice.
Yeah.
I think I need to do a reread.
Yeah.
The chapter, yeah.
Cool. Yeah.
Good.
Sounds good. Yeah, I must have read this chapter before because I had some highlights in there that I found. I don't remember reading it before. So it was good.
Okay.
It was good to read it.
You have a ghost bot that reads your book.
I must. I thought I only got to chapter 6 last time. That was probably about a year, maybe about a year or 2 ago when I started reading this book. And I thought I only got to chapter 6, but looks like I made it to chapter 7.
Oh, okay. Yeah.
Yeah, cool. Well,
All right.